Okay, welcome to the second lesson of the quantities unit, the mole and Avogadro's number. So the difficulty here with what is a mole, so there's this clever little, there's this clever little spy right here, like a mole in an organization or something. A mole is a small animal that burrows in the ground. A mole is a blemish on the skin. But it also relates to the word molecule. So once Avogadro is an Italian scientist, and we'll actually talk more about him in the gas law unit. He said that a container he's particularly focused on gases, had to have the same number of particles if they weighed the same, or occupied the same volume for gases. So he did not know what atoms were. Nobody has really seen an atom, same with us, like what it actually looks like. And so we have to convert between things that we can see in a chemistry lab, like grams, and convert that into dealing with the atomic level as well. So when you weigh out a mass in grams, then mass is a measure of how much that amount of matter takes up, how much space. So if you think about if you had 6 grams of oxygen gas, then that's very different than 6 grams of chocolate or something like that. So grams isn't a great way to convert between units because it doesn't boil down to the same thing. It's how much space the amount of matter takes up, and obviously different things take up a different amount of space. So we needed a way to remedy that. And so chemists decided that they would use Avogadro's ideas about a certain amount of a substance containing the same amount of particles. And their benchmark was carbon. For lots of reasons, carbon's easy to find, so they could easily measure it. So if you look at the atomic mass reported on the periodic table for carbon, it's 12. Okay, so up until now, we've talked about, atomic mass units, and whether you use U or AMU, it doesn't matter. So now what we're going to shift towards more is how can we convert between values that we can see. So atomic mass units is it almost feels like we made it up, right? How can we use that in a lab? How does it make sense? So then the scientists said, okay, well, if they were able to figure out the average atomic mass and all that kind of stuff. So then using carbon as a benchmark, they said if you have 1 mole, okay, so a mole is just a unit of measure, like 1 dozen eggs means 12 eggs. An average class size of students is 30 students. So 1 class is 30 students. So it's just a random sort of measure that is useful in chemistry. And they said that they decided to use carbon. So if you have a sample of carbon that is 12 grams, then that is equal to 1 mole. So we are going to now be able to convert between grams and moles. But then again, if you want to get all the way down to the atomic level, right, why not just leave it as grams? But we want to think about what's happening at the atomic level. So atoms are so small that you can't put 1 atom on a scale in our class and measure how much that is. So we convert between grams and the number of atoms in order to talk about things on a realistic level that we can see, and also consider what's going on at the smallest level of chemistry. And that's really, so Avogadro had these ideas about about quantifying amounts in a different way. And then so he was actually not alive when they really pin down what the number of particles was in an amount that they were going to use. And so we still call it Avogadro's number, but he was already dead by the time he got that distinction. So they use the word mole, a German scientist, basically because it's like a short form for molecule. So a mole is a unit of measure. So it relates to how many particles or how many entities is the word your textbook uses are in that amount of a substance. So now 1 mole of anything is 6.02 times 10 to the power of 23 particles, entities, whatever. So if I go back to oxygen and chocolate, that would mean that there are, actually desks is better. So let's say you have oxygen, which is in the air. If you had 6.02 times 10 to the power of 23 particles of a gas, and think about if you had 6.02 times 10 to the 23 desks, how much space those desks would take up. That's an incredible amount of space. But the gas would actually fit inside a pretty reasonably sized cube. And we actually, unfortunately, we have one in our class. Obviously, we don't have it here. Maybe you've seen it. It's a black box. So the amount of space taken up by a gas is not the same as the amount of space taken up by something like desks, but it doesn't matter. What matters is when you boil down to it at an atomic level, the mole, the unit of measure we're going to use, has 6.02 times 10 to the power of 23 particles. So every single mole of a substance is not going to weigh the same, but it is going to have the same number of particles. So then what we're going to do next in this, after chapter 6, is look at something called stoichiometry. So stoichiometry is going to help us now relate, not just talk about one substance, how can we relate the one substance to something else in a reaction? Okay, so the symbol for Avogadro's number is capital N, small a, and you definitely should memorize this number, okay? Unfortunately as well, you should get to know your calculator. So when you do scientific notation, usually or if you have a friendly calculator, there is often a button that will do the times 10 for you. Because what we're going to do is we're going to multiply and divide using this number. So if you type it in like 6.02 times 10 to the power of 23, if you don't use the scientific notation button on your calculator, maybe it's EXP or EE, then you have to use brackets around the number or else you'll get weird answers like 9 times 10 to the power of 41, which is not what you want. Okay? So get to know your calculator when you are doing the homework. Or maybe you already know. I know Mr. Vine loves scientific notation, which is great. Okay, so in the first lesson, we did talk about molecular weight or molar mass. And in the first lesson, I sort of left the units kind of ambiguous, but it relates to this idea about carbon and the atomic mass that's listed on the periodic table. So that mass can also be called the molar mass or molecular weight. They mean the same thing. So how many grams for 1 mole of substance? So the mass in grams of 1 mole of substance, we're going to use the symbol MW. Okay, so now, and when you do the molecular weight or molar mass, you should include units, and the units are grams per mole. How many grams in 1 mole of substance? Okay, so let's just review molar mass. So because you never have to memorize the periodic table, as long as you have the correct formula, the molar mass or molecular weight is literally it's like it'll become the second nature to you. You'll do it without even thinking about it. I've even had students say to me, "Oh, Miss Todd, I have the atomic mass for oxygen memorized," like they're mad at me. But you don't have to memorize the periodic table, but it's just this step is going to be like one of the easiest. Okay, so Lauren actually burned me on this. There was one of these questions. type of questions in the homework from the other day. This is called a hydrate, which we will also talk more about how you figure this out. And what it actually means is that every copper sulfate has 5 water molecules attached to it. So if you say you hydrate yourself, then you add water. And hydrates are actually really common forms of ionic compounds. Like those of you that have a pool or something that has standing water, you might even use something called bluestone. So that's what this is, copper sulfate pentahydrate, we call it. So what this means is the 5 waters are going to add to the mass of the substance. So if you've ever looked at a chemical bottle, sometimes they'll say anhydrous, which means that ionic compound does not have water molecules attached to it. It's not a hydrate. And so now you'll see that the formula weight or molar mass, molecular weight, is going to be greatly influenced by those 5 waters, and it makes a big difference. Okay, so you have options for this. You can do what copper sulfate is and then add the 5 waters to it. You can, some people, like I said, some people will even start to have the molecular weight of water memorized, which is 18 grams per mole, and then you just multiply by 5 and add it to the copper sulfate. It actually doesn't really matter. Okay, so for now, I won't worry too much about rounding. So I'm going to do, so when you're doing the molar mass of a hydrate, then really what you're doing is you have 1 copper, the mass of 1 copper, plus the mass of 1 sulfur, plus the mass of 4 oxygens. I'm going to put oxy so it doesn't look like a 40. And then now we've got this here. So this is a big number. It's a coefficient. So you multiply. So like 5 times 2 and 5 times 1. Okay. So you can certainly do it that way. Like I said, some people, eventually you might choose to find copper sulfate and add then 5 waters to it. Like you'll have that memorized, but it doesn't really matter what you do. Okay, so 1 copper is 63.55. So again, now we're going to use the units, grams per mole. We're not going to use AMU anymore, or U. Sulfur is 32.06. Oxygen is 16 right on, but we have 4 of them, so we have to multiply by 4. And then 10 hydrogens and 5 oxygens. Okay, so this, you don't need to simplify it. Yes, there are 9 oxygens. Yes, you could have put that together, but really it doesn't matter what you do. So you should end up with 249.69 grams per mole. Again, if you want to get full marks, make sure you have units. Okay, so that means that each copper sulfate pentahydrate is 200, each 1 mole of that would weigh 249.69 grams. So that is a very heavy substance, so which is common with ionic compounds. Okay, so now how we want to convert between grams and moles, because eventually what we're going to do is take those moles and then actually find the number of atoms. So again, getting from a gram amount that you can see and measure and use in the lab to what's happening at the atomic level, which we can't see. Okay, so there is this formula here. If you are a triangle person, okay, so it's mass over molar mass. So this line is the divide line, and that's the multiply line. If those of you that are interested in taking or thinking about taking the AP exam, then they'll give you the formula like this, but you really have to use dimensional analysis. They're not going to give you triangles. Okay, so just keep that in mind. But for most of us, using the triangle is perfectly fine. I left on the on D2L, it says the first file listed is a formula sheet for the whole unit. So usually I would have given that out for we usually write quizzes and then write a unit test. So those formulas you can print that formula sheet off if you want when you're doing the homework to help you. That's why I left it up there. Okay, so the units for molecular weight are grams per mole. And again, you're using the periodic table. If you use a different version, you might find they have different rounding in the average atomic mass reported. That doesn't matter. And then N is the number of moles. So chemists in general, I find, are a little bit lazy. So the unit that we use is MOL. So the word mole minus the E, okay? If you choose to write out the word mole, that's perfectly fine. And then when you do the mass, it has to be in grams. So if the textbook or homework or whatever gives you a question in kilograms, then you would have to convert it. So just be careful with that. Okay, so now, so this is a pretty straightforward formula. If you have, again, for dimensional analysis, then we have, if you have mass and you're going to divide by grams per mole, then really what you're doing, you have to invert and multiply. And then once you do that, the grams cancel out and you're left with moles. Okay, so that's where you get the relationship from. So all of these, dimensional analysis, using the formula that's in the cloud there, or using the triangle, are all perfectly reasonable in this class. Okay? All right, so let's do a simple example. A sample contains 1.25 moles of nitrogen dioxide. Oh, I forgot to say, so for whatever reason, they use the symbol N for moles, like lowercase n. So far we've got Avogadro's number is N, capital N, little big A. Then we have molecular weight, which is MW. Then we have N for moles, and then mass in grams. You've seen that before when you did density in grade 9. Okay, so if it helps you, you can write out your data. So it says 1.25 moles. So that's 1.25 moles. What is the mass of the sample? So it almost looks like we are missing something, but again, it's going to be second nature for you to calculate the molecular weight to find that, because you don't have to memorize the periodic table. So nitrogen dioxide, you do need to remember that it's NO2. So we've got 1 N and 2 oxygens. And moving forward, this step, I wouldn't even actually expect you to show this step. You could write your answer for the molecular weight. You don't even need to show the calculation. But I will here. Okay, so remember 2 times 2 oxygens, because there are 2 of them, gives us 46.01 grams per mole. Okay, so if you are a triangle person, I'll do that one first, and then I'll divide the page. I'll do the non-triangle way on the other side, in case you don't like triangles. Okay, so we are finding mass. That's what we're looking for. So that's the top here. So that means we're going to do moles times molecular weight. And I don't care if you include units in your calculations, but you do have to make sure you have the correct unit in your answer. And so again, dimensional analysis sort of works here, because you can there's a mole in the top and a mole in the bottom, so they cancel out and you're left with grams. Or you could simply just remember that moles is, that mass is in grams. Okay, so you can also do this and not use a triangle. So now you're solving for m. To get rid of the 46.01, you have to multiply. So you would multiply on both sides. I'm squishing, sorry. Okay, or again, if you want to do even different dimensional analysis, it's the same thing. Okay. So converting between moles and mass is really going to be one of the easiest things eventually that you'll do. I know right now it's like, what's a mole? A mole is just a unit of measure. You're just trying to get down to what we want to do next, which is how many molecules or how many particles, and then how many atoms are there in a sample. So really down to the nitty-gritty of the chemistry. Okay. So to calculate, like I said, your textbook uses the word entity. So to calculate the number of entities, you are converting between entities and I think this should be moles, using Avogadro's number. And the textbook uses entities as a general term because we did talk about this when we did covalent compounds. Molecules, it should be reserved only for covalent compounds. So they use the word formula unit for ionic compounds. So when you have a metal and a non-metal. But to be honest, let's say you're into, if you Google mole to atom worksheets, you would find a million online. So if you're into that, then you might find that they just use the word molecules for everything, that's not necessarily what they should do. However, that is what they do. So again, when you have, back to the definition from here, so this is in 1 mole of a substance, you have 6.02 times 10 to the power of 23 entities. Entities per mole. So when we do per, you write it in the bottom. And then, so in order to convert between moles and entities, then you want to cancel that mole out. If the moles is in the bottom, how do you cancel it out? You multiply. So if you prefer formulas, which again is really fine for this scope of this class, the number of entities is the number of moles times Avogadro's number. You could even make that into a triangle. If you prefer that. And I'll write this, that's a symbol here again. Okay, so we're going to continue our same sample, 1.25 moles of NO2. How many molecules are in the sample? So again, they're using molecules because this is a covalent compound. You can use the word molecule if you prefer the word entity. Sorry, that's terrible. Hold on. Okay, it's all the same thing. It's just very particular. Okay, so the number of molecules. Again, if you are a triangle person, so we're looking for the top of the triangle here, number of entities, so we're going to multiply. Or you could, again, do dimensional analysis. So when we have 1.25 moles, which we're given, it's right here, and you have always 6.02 times 10 to the power of 23 molecules, no matter what you're talking about, in 1 mole. Or you can even think of it like, say it out loud. Okay, so 6.02 times 10 to the power of 23 molecules in 1 mole, but I actually have 1.25 moles. That means that I should have more molecules. So you can even think of the logic of your answer that it should be a little bit bigger. So when you multiply these together, you get 7.525 times 10 to the power of 23 molecules. Oops. Okay, so a little bit bigger than 6.02 because we have greater than 1 mole. So if we had half a mole, then you would get a number that was half of 6.02 times 10 to the power of 23. So sometimes students like the quantitative side of chemistry because you can figure it out and it actually makes sense. Okay, so now we're going to move on to the number of atoms. So again, this is for covalent. And then if it's, which really it's the same thing, but if you have an ionic compound, it's going to ask you for the number of ions. Okay, so you have counted atoms before, right? So we have 1 nitrogen atom per molecule. Based on that, we have 2 oxygen atoms per molecule. And if we did the total, we have 3 total atoms, 2 plus 1 is 3, per molecule. Which is fine when we were balancing because we were, just trying to match them up to the other side. But now we're saying, well, in our sample that we were just talking about, how many molecules did we have? Well, we had 7.525 times 10 to the power of 23 molecules. So when you're converting to the number of atoms, again, you're going to multiply. So this is really, I find that students mess this up the most. Again, maybe it's because the numbers are going to be in scientific notation. There is no calculator that will display a number like 6.02 times 10 to the power of 23 without using scientific notation. So there is that. But, don't stress too much about it. It's really a very straightforward calculation. Okay, so when you're calculating the actual number of atoms in your sample, not just in one random molecule, I will specify again because your textbook will. So you're going to take how many molecules you have, or formula units or whatever, number of entities, and then the number of atoms or ions in one entity. So again, if you're looking for the number of atoms, the entities would cancel out, and that's what you would be left with. Okay, so here we have this again, we're just continuing with our example. We got 7.525 times 10 to the power 23 molecules of NO2. And it says calculate the number of nitrogen atoms. And it doesn't matter when you multiply which one you do first. So if it in your brain, you think of, okay, I have 1 nitrogen atom per molecule first. It doesn't matter. I'll do it both ways. And I have 7.525 times 10 to the power 23 molecules. I realize this is the same number, but let's just show it work. Okay, the molecules cancel out, and you're left with the same answer. But now over here, now we're going to do oxygen. Okay, so I'll write it like the formula I did. So you can see, it doesn't matter. so we're still talking about NO2. How many oxygens are in one? There are 2 oxygen atoms in one molecule. So how do you get the molecules to cancel out? You multiply together, actually. And then the number of total atoms. So if we have NO2, again, you've got 1N plus 2O equals 3 total. Okay, 3 total atoms per molecule. So the molecules cancel out. And again, now you're just multiplying and you get 2.2. I'll just leave all the digits for now. Okay, so that is a very broken down way to do it. So what we're going to do is we're going to do a couple of less easy examples, it says. But so what happens is you can't skip steps. Okay, so maybe don't write this down until I'm done so you can see what it's going to look like. Like if you are going to get all the way down to the atomic level, then you need the number of entities first. If you have mass because you've measured that in your labs, then you have to always convert mass into moles. Okay, so this flow chart, kind of dictates the steps that you have to take in a question. So if you're given mass and it asks for atoms, for example, then you would have to convert mass into moles first, and then moles into entities using Avogadro's number. And then the last formula we just did to change it into atoms. Okay, so this is not easy to write, sorry. Okay, so that goes there, sorry. Okay, so again, on that formula sheet, there is a flow chart listed there without the formulas in it, but so that if you, depending on what you're given in the question, then that can help you formulate which formula you're supposed to use. Okay, so take a minute and pause the video and write that down. Okay, so now I chose this example because, again, it uses the word like your textbook uses, formula units, but really we're still talking about the number of entities, but now because sodium chloride is a ionic compound, it uses the word formula unit. And also what happens when you do this formula, this is where, again, you want to make sure that your that you have a good relationship with your calculator. So we're asked for the number of moles, and Avogadro's number is always 6.02 times 10 to the power of 23. So now to isolate n, we actually have to divide, right? On both sides. Here it cancels. So now you're doing 4.56 times 10 to the power of 19 divided by 6.02 times 10 to the power of 23. So if you type that in your calculator without using the scientific notation function or brackets, then your calculator will screw up the bed mass. All right, so you need to be careful with that. You should get this number, or if you like scientific notation, I don't care. Either answer is fine. So again, use brackets or use the EXP or EE button in order to do the times 10 for you. Okay? So give that a try. That one really is just the wording of the question. Again, that formula units is the same as entities, and practicing dividing. Okay, so now this one, it says less easy example number 2. How many hydroxide ions are in a sample of 0.35 moles of iron 3 hydroxide? So we're given moles, and we want to get to the number of ions, which you can't skip steps. So we're missing a piece here to get to the number of ions. We need the number of entities. So this question is going to have more than one step. So we have to find or convert moles to entities first. And so again, whether you like the formula or you like the triangle, it doesn't matter. If you like the word entity, or if you prefer to use the word formula unit, both of those mean the same thing as well. So we're given the number of moles. Avogadro's number, you're going to remember forever. And you're going to practice using scientific notation numbers in your calculator. Okay? So formula units or entities, it doesn't matter. But that doesn't get us to the number of ions. And it says, read the question carefully. Hydroxide ions, which is OH. And so we have how many hydroxide ions are there in our formula unit or entity? There are 3. How many entities do we have? Well, there it is. So let's say, if we are able to ever really write real tests, let's say you got, this was part A or something, and this was part B, or even step 1 and step 2, and you got this number here wrong, then as long as you carried your mistake through correctly, I would not take marks off twice. So always show as much work as you can in order to get part marks if you're worried about it. Okay? So you just multiply, the entities cancel out, and you're left with the number of ions. Okay? And so there are quite a few questions for homework. I'm not gonna, this usually moles, we would do a bunch of activities with the moles, with the mole as a quantity before we would move on. So take some time and do as many of these practice questions as you can. I'm gonna post some other videos that people have put on YouTube that I didn't mind. They, you know, again, try to give you a visualization of what we're talking about. I'm also going to post a worksheet that I in the past have given out. I don't always, but it really goes through things step by step if you find that the homework is, it's hard to know what to do. And so when you go through the questions, like these are a certain kind, these are a certain kind, these are a certain kind, and then these ones are the ones that are all mixed up together. So they are definitely, you know, like save those for the end. And then it's helping you to try to decide what type of question to do. If you have any questions at all, please email me. Okay? And have a great weekend and get some rest.